Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Newton's Divided Difference. Newton's divided difference is a method used for interpolating a polynomial through a set of given data points. The method is based on recursive computation of the divided differences, which are used to find the coefficients of the interpolating polynomial. By constructing a divided difference table, one can easily compute the polynomial that fits a set of data points. It's particularly useful for constructing the Lagrange interpolating polynomial, but it is also used in numerical methods like finite difference methods for approximating derivatives. Consider a set of discrete data points xk, fk for k equals 0 through n, and an interpolating polynomial of the following form, where ak's are the unknown coefficients. The polynomial satisfies the interpolation points, so imposing fxk equals pnxk equals fk for all k gives n plus 1 unknowns. Setting x equals x0 in the polynomial approximation gives a0 equals f0. Setting x equals x1 in Pnx gives a1 as follows. Setting x equals x2 and utilizing a0 and a1 gives the following. Continuing in this fashion, the rest of the coefficients are obtained as complicated expressions of xk and fk's. There is an easy way to reproduce the coefficients by employing the concept of divided differences. The divided differences are defined as differences starting from the zeroth to nth divided difference. The zeroth divided difference is the discrete function value x equals xk. Making use of this expression, the first divided difference can be expressed as follows, which is also symmetrical. The second divided difference can be written as. This process is continued in a recursive manner, yielding a general recurrence expression for the nth divided difference as follows. The coefficients then are expressed as shown. A divided difference table is used to compute the divided differences systematically. A simple way to construct the divided differences for Newton's interpolation formula is to use the recursive relationships to generate the divided differences through the Newton's divided difference table. The table is filled in a triangular manner. Firstly, the original data set is placed in the two columns. Each subsequent column calculates the divided differences based on the values in the previous column. The divided difference for 2 points, xk and xk plus 1, is calculated and placed in the third column as follows. For higher-order divided differences, the recursive formula is applied until all divided differences are computed for the highest order. The final form of Newton's interpolating polynomial is written as follows, or in the nested form as follows. Newton's divided difference table depends on the ordering of the abscisses. The interpolating polynomial, unlike Lagrange interpolation, can be easily updated as interpolation points are removed or new points are added. The divided difference table can be extended to include the new additional differences without requiring reconstructing the table from scratch. Strictly speaking, when the interpolation formula is expanded and simplified, all orderings yield the same unique interpolating polynomial. This method, unlike Lagrange interpolation, allows us to add new data points without recalculating the entire table or polynomial. For example, the reconstruction of the divided difference table upon adding new data, x4, f4, to an existing set is depicted in the following table. This process leads to computing the divided differences and filling in the last spot of each column in the table. Starting with the first-degree interpolating polynomial for any x, the degree of the interpolating polynomial can be increased recursively by adding new terms. A series of low-degree interpolating polynomials can be expressed as follows, where P1x, P2x, and P3x are linear, quadratic, and cubic interpolating polynomials. For smooth functions, the added term decreases as the degree of the polynomial increases. A polynomial passing through n plus 1 interpolation points has a degree of n or less. When expanded into traditional polynomial form, Newton's interpolating polynomial exactly reproduces Lagrange's interpolating polynomial. Thus, the error term of Newton's interpolation polynomial is the same as that of the Lagrange interpolation polynomial. This means that if a set of discrete data is truly represented by a polynomial of nth degree or less, the error will be zero regardless of x. The interpolation errors are smaller near the endpoints of an interval, xk to xk plus 1, between two consecutive interpolation points and larger roughly towards the middle. The advantages of the method are: the method can be used to construct an interpolating polynomial of any degree, so long as there are sufficient data points. The interpolating polynomial resulting from the method provides greater advantage because it lends itself to nested multiplications. It is efficient and stable, and it allows adding more data points to obtain a higher degree interpolating polynomial without discarding the existing data. A low-degree interpolating polynomial can yield very accurate results if the data is smooth. The disadvantages of the method are: the method is a bit difficult to understand and implement. It is expensive and impractical for interpolating large data sets. It is sensitive to the errors in the data set. It may lead to inaccurate results when the data points are closely spaced or when the discrete function is highly oscillatory. Estimating the error bounds is not easy. The errors outside the data interval increase uncontrollably, and it is too risky to use it for extrapolation purposes. As a note of caution, keep in mind that a discrete dataset contains noise or experimental errors. Hence, the interpolating polynomial that passes through every available data point becomes tainted due to the inclusion of the errors in the interpolating polynomial. In this regard, trying to include every data point in the polynomial may not be such a good idea. Now, as an example, let us consider deriving the Lagrange basis polynomials and the Lagrange interpolating polynomial for the given dataset. Then, we will estimate the function for x equals 1.2, 2.5, and 3.25. We will first construct the divided difference table. The indices starting from 0 are placed in the first column. The abscissas, i.e., xk's, are placed in the second column. The corresponding function values, i.e., fk's, are placed in the third column. We will now construct the table by computing the first-order divided difference, that is, fxkxk plus 1, and place the results into the third column. The first element of the fourth column is fx0x1, which is calculated as follows. The second element of the fourth column is fx1x2, which gives minus 1.4. The third element of the fourth column, fx2x3, is obtained as minus 3.4, as shown below. The fourth and last element of the fourth column, fx3x4, is calculated as follows. We cannot further calculate first-order differences due to the lack of data. The second-order divided difference, fxk, xk plus 1, xk plus 2, is computed using the first-order differences in the fourth column and abscissas of the extended x-interval. The first element of the fifth column, fx0, x1, x2, is calculated as follows. The second element of the fifth column, fx1, x2, x3, is obtained as shown. The third element of the fifth column, fx2, x3, x4, is calculated as follows. And we finally reach the end of second-order differences. The third-order divided differences, denoted as f, xk, xk plus 1, xk plus 2, xk plus 3, are found using the following divided difference. The results are placed into the sixth column as shown. Finally, the fourth-order divided difference, denoted by f, xk, xk plus 1, xk plus 2, xk plus 3, xk plus 4, is calculated using the following divided difference. Once the divided difference table is completed, we can construct the Newton interpolating polynomial. The coefficients of the polynomial are in the first row, which we identify as a0, a1, a2, a3, and a4. We use the following polynomial as for the approximation to fx. Substituting the numerical data for x equals 1.2, we obtain 3.27206. For x equals 2.5, we obtain minus 0.64. And finally, for x equals 3.25, the interpolated value yields 1.44766. We note that when the interpolating polynomial is put in the simplified form, the result gives the simplified version of the Lagrange interpolating polynomial. That is all for now. See you next time with another topic. Bye.